everyone. So it turns out that the last session we have, the problem solving session for the sixth week, it turns out that there was some technical glitch in the recording software in my end, so the video was unable to capture my audio. So to compensate for that, I will briefly discuss the model assignment problems I discussed in that session, so that it would be helpful for you to uh, solve the actual assignment questions. So let us first start with the first question here. So I'll ignore this brief discussion I have based on the week 6 content, because you can always find it in the course material itself, so no point of going through them. So let's get ourselves to that model questions. So first one is concerned about identifying the invalid resource allocation configuration for PDCC transmission. So there are multiple options throughout the PRBs across two symbols. So as it turns out, we have seen in the course that it turns out that number of PDCC resource bits that you were allocated, their numbers are finite, right? I mean, I cannot transmit any arbitrary number of bits via this code set or control resources. Those are reserved for the uh, PDCCA chain. So therefore, what are the number of bits that are allowed? First is 108, second is 216, 432, 864, and 1728. Basically, you can see it's a multiple. So we have seen 108 is the minimum number of resource bits that can be allocated for carrying a user's downlink control information or DCI, and it can be multiplied up to 16x, that is 1728. So we can write it at like this also. This is 1, this is multiple of 2, this is multiple of 4, this is 8, and this is 16. And this 1 2 4 8 6, we also call it ALs. ALs here refer to aggregation levels, right? So this many bits, these are the fixed number of bits that are allowed. In other sense, these are the valid resource allocation, valid number of resource bits. So here we are given certain number of PRBs across certain symbols. So what we need to look for is, we have seen that one REG or resource element group consists of 1 PRB across one symbol, right? And that is 12 subcarriers. Now when we talk about 12 subcarriers, 3 are reserved for DMRS, right? So basically, uh, one REG is one PRB in one symbol, right? That is what one REG is, and that means 12 subcarriers. And we know that 3 of them reserved for pile up transmission, that is nothing but the DMRS. So how many we are left with? 12 minus 3, that is 9 resource elements you can call. And what is the modulation scheme used here for PDCCHN? It's QAM, right? So for every 9, for 9 REs, how many bits we can transmit? 9 times 2, right? Because QAM means you can transmit 2 bits per symbol, and one subcarrier carries one symbol, so it's 9 cross 2, 18 bits you can accommodate in one REG. And what is the next hierarchy for PDCC transmission? It's CC, right? One CC consists of 6 REGs. So when you multiply 18 with 6, we'll find the number 108. So if I have to find the number of PRBs, so how can I find it? So basically you have total number of bits 108, 216, 432, you need to divide by 18, right? Because then it's going to give you total number of subcarriers. And it turns out when you divide this set with 18, you will get this 6, 12, 24, 48, and 96. So these are the possible number of PRBs that is allocated for resource bits in PDCCA chain, right? So now we have to see whether these are matching. Like for example, here 13 PRBs across two symbols, so total 26 PRB. So 26 is not part of this, right? 26 is not here, so it's not a valid resource allocation configuration. Second option is 9 PRBs across two symbols, that makes 18. So 18 is also not part of this, so that is also invalid. 10 PRBs across two symbols, that is total of 20 PRB, but 20 is not included also in that set, so that is also invalid resource allocation configuration. And the fourth one is the 8 PRBs across two symbols, that is 16 PRBs. So 16 is also not included in the set, so this is also a invalid resource allocation configuration. So the only configuration that would be valid would consist of total number of PRBs that will match one of the numbers in this set, 6, 12, 24, 48, 96. Then only it's a valid resource configuration, otherwise it's not. So in this question all the options are going to be incorrect only. Now we move to the second question. Now it's given that user is assigned 6 PRBs across two symbols to receive a PDCCA signal with DCI length of 42. Then we are supposed to calculate the length of polar encoder. Now we see polar encoder length, that is capital N here, can be in power of 2, that is 2 to the power some integer n, where the minimum value is n is 5 and maximum is 9 when you talk about downlink DCI. Now it turns out when I say the length of the polar encoder, here I mean the capital N here, right? So how do I solve this question here? So you can see that DCI length is given 42, let's call it K, and the resource bit let's consider it to be capital E, okay? So what is the code rate for this particular scenario? It's DCI plus CRC, right, divided by resource bits. And how do I calculate the numbers, the length of the polar encoder? So it turns out, if the you remember the polar encoder, the mother code rate is 1 over 8, right? So if I use this expression, this code rate, you replace by 1 over 8. So therefore we can get the resource bit number, right? Resource bit number turns out to be 8 times 42 plus 24. Why 24? 24 is a 24 bit CRC that is appended to the original downlink control information. So that is what the number you get from the resource bits you require, and it turns out this number is going to be 10. I mean here I mean number, not this capital N, I mean by small n here, and we get it 10, right? We keep it as it is. Next, so this comes from the concept that this polar encoder length depends on two things. One is your code rate and second is the resource bit allocated to you. So we have already calculated that if the mother code rate is 1 over 8, how many resource bit there should be? It should be 2 to the power 10 or 1024. We'll come to that why it's not possible, because we have already written here that for downlink DSI the nmax value is 9, that is 2 to the power 9, but we'll come to that later. The second thing is, what is the number of resource bits that is allocated? That is already given, right? 6 PRBs across two symbols. That means how many PRBs? Total 12 PRBs. Total 12 PRBs, and each PRB has 9 resource elements because 3 is reserved for DMRS, so 9, and each symbol carries 2 bits. So total number we are getting here is 216. So that we calculate separately as n2, and we find out that number to be 8, right? Because we are applying ceiling operation, log base to e comes out to be 8. This is the number n we get, that if we only consider the uh, dependence of polar encoder over the code rate. So we have this 42 plus 24 CRC appended DCI length we need to have a mother code rate of 8. So basically our my uh, if I need to have a mother code rate of 8, I need to generate 2 to the power 10 or 24 1024 bits, but my number of resource allocated is 216. Applying by seeding operation, we get n2 as 8, right? N1 as 10, n2 as 8. And what is the formula here? You see, we have to, if we don't go into the formula and things little bit intuitively, so to satisfy this mother code at 1 over 8, I need 1024 bits to be generated, but the maximum limit is 512, right? So how can I get that? I'll put minimum of this number with 9. If the number crosses 9, it's going to be 9, like if it's more than 9, and if it is less than 9, then it would be just that number. And what is the number we should choose between n1 and n2? N1 is the number of bits to be generated to support the mother coordinate of 1 by 8, and n2 is the number of resource bits that is allocated. We are supposed to choose the minimum of it. So once we get that number, but it turns out that n mean cannot go below 5. So how do I ensure that? I basically take max of that number with 5, so that whenever the number falls below 5, it would be automatically assigned 5. If it's over 5, then it would be assigned that number. So if we apply this formula, it's mean of n1, n2 and 9, and outside you have a max with n mean, that is 5. So if we put these values, n1 as 10, n as 8, we get that entire output as 8 here. So it's 2 to the power 8, or that is 256. Or if you talk about capital N, and if you talk about small n, then the answer would be 8. So none of the options are actually correct here. So I hope you understand the concept of n1 and n2. N1 is in the case if if only if the polar encoder length depends only on code rate, then you will get n1. That is, you have CRC appended DCI length as 66, then we have to generate 1024 bits to satisfy mother code rate, and that is how we get n1. But that's not your answer, that is one value you just keep, and n is the number based on the number of resource bits allocated to you, that is 216. And now you take minimum of it, and of course you have to ensure that this number should not cross 2 to the power 9, or if you talk about small n, it should not cross 9, because the maximum, that is what allowed. So we take min of n1 n2 with 9, and then you outside you put a max, because the minimum length cannot go below a certain value, that is 2 to the power 5, and then you obtain this expression here. So that's how we are obtaining it. So we can see that basically it comes from n depends on one thing, code rate, second is resource bit. So code rate, the dependency on code rate gives me this expression, from where I calculate n1, and the dependency of resource allocated resource bit, uh, let me calculate n2. We keep both this number and we put in this formula, and we get whatever output this is. For this case, it turns out to small n as 8 and capital N as 2 to the power 8 or 256, as none of the option matches here, so none of them are correct. So even if I have written here resource bit, don't confuse with the resource bit E given here, because this is resource bit E here actually talks about the allocated resource bit, and here what I mean by resource bit is basically what is the number to ensure that mother code rate of 1 by 8 is satisfied. So I should call it by a different name, not exactly resource bit. uh, what should I call it? Okay, let it be resource bit as of now, but don't confuse it with the E here is basically the resource bit allocated for the transmission of PDCCS signal, and here is the one you can call it pseudo resource bit, in the sense that is it is not the actual resource bit, it's the number that is used to uh, that basically denotes the number of bit you need to generate to satisfy the mother code rate. So next question is about the extension of the previous one. It basically asks that what is the rate at which the PDCC signal is transmitted from the previous case, and we have already obtained the number of resource bit allocated, we have calculated as 216, and what is the number of message information, that is the DCI plus 24 bit appended CRC, that is 66 over 216, and that turns out to be 0.3055. This question is again 6 PRVs across 2 FDM symbol. Then what is the DCI length should be for which shortening will happen during rate matching? Now whenever you hear the term shortening here, what is the criteria of shortening? So first of all, your n should be greater than e, right? That is the number of bits you have generated at the output of full or encoder should be greater than the number of resource allocated, number of resource bits allocated, because in that case you have to drop certain number of bits. And what is the criteria for when do you do shortening or remove the bits from the end? When your rate is basically higher than, greater than, higher than 7 over 16, right? So I know already 6 PRVs across 2 symbols mean there are total how many bits are allocated? 216 bits are allocated. And what is the rate expression? If I consider the DCI length to be x, it's x plus 24 over 216 as r. So by this formula of shortening, this ratio should be greater than 7 over 16. Now we proceed to the calculation. It turns out to be x greater than 102. Now if there is no option, then the answer should be like this, that x need to be greater than 102. This part we have already obtained from this expression here. And what about this part? You remember the for downlink DCI, the maximum DCI length is always 140 bits, like, so it should be in this particular scenario the number of DCI bits should be between 102 to 140 to ensure the shortening is happening during rate matching. Second, ask basically about what parameters help user to identify the location of user specific search space, and intuitively you can see that it's for a user specific search space, something that is user specific will can only have. And what is user specific? You can see here, that is the CRNTI, that is unique for each user. So that is explicitly used by Gnode B to provide the information of user specific search space. So about the 10th question here, what should be the maximum number of blind decoding attempt user has to make in a slot if its search space consists of 16 CCs per OFDM symbol across 3 OFDM symbol and has the following core set. So basically you have mentioned that you have 16 CCs per OFDM symbol across 3 OFDM symbol, just a minute, okay, 4th, 5th and 6th, and you are allowed 2 aggregation levels 4 and 8. So how do you calculate that? First we will talk about aggregation level 4. So per symbol 16 CC is allocated. At aggregation level 4 you have to consider 4 at a time. It can start at 0, 4, 8 and 13, right? Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So it can aggregation level 4, there are only 4 possible combinations. So per symbol there can be 4 candidate, and we are talking about the core set consists of 3 symbols, so it's 4 times 3, so user need to make 12 attempt for aggregation level 4. And of course when you talk about maximum number of blind decoding attempt, when it will happen? Only when the users decoding users corresponding PDCCH is at the end of the highest aggregation level. So at aggregation level 4 it has to make, there are 12 candidates, PDCCH candidates, each symbol there are 4 candidates, so it will make 12 attempts there. At aggregation level 8 you are only allowed to start at 0th and 8th symbol. So there are only two possible candidate per OFDM symbols, that is 16 over 8. And when you talk about three symbols, there are total of 6 attempts. So at aggregation level 4, user will make 12 attempts, and aggregation level 8, user will maximum make 6 attempts. So total 12 plus 6, 18 attempts it has to do to find its PDCCH uh, information. So maximum 18 attempts here. If we talk about, if here another aggregation level is added, that is 16, then it would be one candidate per symbol, and one cross three across three symbol there will be then three more attempts. So it would be in that case 18 plus 3, 21 attempts. But since the aggregation level uh, 16 is not involved here, so only 4 and 8, so there are only 18 attempts. And if the 8 is not there, only aggregation level 4, then in that case it will be only 12 attempts. So we have to be careful about how many aggregation levels is a part of your course set. The second question is about, again, a course set configuration is given 32 cc's per OFDM symbol across two OFDM symbol, which is given at the fourth and the sixth one. Fourth and the sixth one, and what is given, if the subcarrier spacing is 15 kilohertz, then you are supposed to find the valid L configuration, right? So first of all, you need to consider how many blind decoding attempts user can make, and that depends on the subcarrier spacing, right? For 15 kilohertz, there are total maximum of 44 attempts, right? Now let's start with the first option, that is L. Okay, first we calculate the number of PDCCH candidate at different aggregation levels, and then we will compute. Then we will see which of the um, aggregation level configuration valid or invalid. At aggregation level 2, part symbol there are 32 cc's, so it need to be divided by 2. So there will be 16 PDCCH candidate per symbol, and in two symbol there will be 32 PDCCH candidate. So for aggregation level 2, user have to make 32 attempts. At aggregation level 4, similarly there will be 8 PDCCH candidate per symbol, 32 divided by 4, that times 2 symbols, so total 16 attempts at aggregation level 4. At aggregation level 8, similarly you will have 8 attempts, and at aggregation level 16 you will have 4 attempts. So let's talk about first aggregation level configuration, that is 8 and 16. So if we pick 8 and 16, there are 8 plus 4, total 12 attempts, that is well below 44. So 8 plus 16 is a valid combination. Then let's talk about 2, 4 and 8. So in 2 there are 32 attempts, in 4 there are 16 attempts. So if I only combine 2 and 4, it's becoming 48, even without considering 8. So 48 is more than 44. So L248, aggregation level 2, 4 and 8 are not a valid combination, because you are surpassing the maximum number of attempts that are allowed. 32 here, 16 here at 2 and 4, and if you join 8 here, that is another 8 attempts, so total 56 attempts, that is well beyond the 44 attempts. So that is not a valid aggregation level configuration for this particular course set. Let's talk about 4, 8 and 16. 4 there are 16 attempts, 8 there are 8, 24, and 16 another 4, so 28, total 28, that's below 44, so that is also a valid attempts. And aggregation level 16, of course there are only 4 attempts, which is also below 44, so it's a valid. So 1, 3, 4 are valid aggregation level configuration, while the second option is the invalid configuration. You need to be careful, you need to process the key information here. What is your subcarrier spacing, that will decide your number of maximum number of blind decoding attempts that you can make, and then you compute your aggregation different number of PDCGH candidate, you can call it attempts also at different aggregation level, and then you have to go through carefully the aggregation level combinations to find the answer for your case. So this question here talks about a 5G NR system with 100 MHz of bandwidth and 60 kHz of subcarrier spacing, and G0B uses the first 128 PRBs across each OFDM symbol in a particular slot only for sending DCI with a course set design as shown below. So what does that mean? So you are using 128 PRBs across each symbol, that is you are talking about one slot, and you are using all 14 symbols to sending DCI and using all 128 PRBs. And the course set design is given as follows: you are sending 2 FDM symbol at AL1, 4 at AL2, 3 at AL4 and 2 at AL8. So remaining symbols, how many are remaining? The total is 11 here, the remaining is 3, so 3 symbols at AL16. Now you are supposed to calculate the maximum number of users whose DCI can be sent per second if course set has a duration of 1 FDM symbol with a period of 8 slots. So important point to note here is the maximum number of users or DCI can be sent. How do you compute that? Basically you need to see how many PDCCH candidate is possible. How many PDCCH candidates are possible. So these actually depicts the maximum number of users whose DCI can be sent. Now if we talk about 60 kHz subcarrier spacing, a slot duration is 0.25 millisecond, right? So per second you have 4000 slots, and you are sending course set duration of one FDM symbol with a period of 8 slot. So when you talk about 8 slot here, and in the second there are 4000 slots, and you are sending code set every 8 slot, so that means you have slot that carries the code set that is mentioned here, the number is 500 here. Okay, so the number is 500. So that we solve that. Okay, whatever number we get, whatever number of candidates we get per slot, we just need to multiply with 500 to get the number of candidates per second. Now we can focus on per slot basis. So it turns out at aggregation level 1, how many you can, how many candidates are possible. So its total PRBs is 128. 6 PRBs, that is PRB across one symbol, consist of 6 REGs, that makes 1 CC, right? That is the smallest unit over which a one user DCI can be sent. So what is the total number of candidates at aggregation level 1? It's 120 over 6. You have to do the floating operation times 2 symbols. uh, yeah, times 2 symbol, and there would be 42 candidates, right? Similarly at aggregation level 2 we have 40 candidates, aggregation level 4 we have 15 candidates, aggregation level 8 we have 4 candidates, and aggregation level 16 we have 3 candidates. So if we sum them all up, it turns out total number of candidates or total number of users per slot comes out to be 42 plus 40 plus 15 plus 4 plus 3, that is 104. And once you calculate the number, you can just multiply with 500 to get the number of users that's whose DCI can be scheduled per second, and the number comes out to be 52,000 here. And lastly, we are given this question: user is assigned 24 PRBs across 2 FDM symbol to receive a PDCC signal. Then the question is, does any valid DCI length exist for which shortening will occur during red matching? So what you need to do, you need to calculate the number of resource bit allocated. That you can easily calculate because you are given the number of PRBs and how many symbols are there, and you already know how many symbols per uh, sub yeah, how many symbols per PRB you can, how many bits per PRB you can transmit. So that turns out to be total number of resource bit as 864. Now note that number down, and in downlink DCI you know that maximum polar encoder output length is 512. So criteria of shortening, the first criteria is your polar encoder output length should be greater than the number of resource bits allocated, right? But it is not the case, right? It's the opposite. Shortening will happen when the output of the polar encoder is greater than the bits allocated. So in that scenario you need to drop certain number of bits, but here the number of bits that is allocated is more than the output of polar encoder length, so basically you have to repeat. So there would be no shortening at all. So therefore the answer is the no valid DCI length exists for shortening to happen, because the fundamental criteria of shortening is that output of polar length n output length of polar encoder n should be greater than the number of bits allocated. But here the scenario is quite opposite. the number of bits allocated is more than the output of fuller encoder length. So therefore no valid DCI length exists for the same. So this is it. This is the crux of the model question discussion that I did in the last problem solving session. I apologize for the voice not being recorded. I'll be careful next time. And with that, I will conclude this session, and I'll upload this in my channel as a supplementary to that previous discussion. Thank you all.